Welcome back. In our last few discussions, we explored two significant advancements: flash attention and the scaling laws paper. Enough. Remember how flash attention tackled the speed and memory challenges of self-attention, and scaling laws guided us on balancing model size, data, and computation? Today, we're diving into another crucial development: low-rank adaptation, or LoRA, which was introduced in 2021. It's a unique strategy for fine-tuning large models more efficiently, and I think it ties in well with what we've discussed so far. What do you think?
Absolutely. Even though LoRA came before flash attention, it's interesting to revisit it now, especially since it aligns well with those concepts of memory optimization and scaling. It seems like LoRA contributes to making models not just bigger, but smarter in how they adapt to new tasks.
Exactly. LoRA's importance lies in its parameter-efficient fine-tuning. It introduces low-rank decomposition to reduce the number of trainable parameters. This makes it possible to adapt models with far less memory overhead. What's your take on this, considering what we've learned from flash attention and scaling laws?
I think it's a logical next step. Keeping the pre-trained weights frozen during fine-tuning sounds like a clever way to improve efficiency. And from what I understand, it doesn't add any inference latency, which is a big win for real-time applications.
You've got it. That's one of LoRa's standout features: no additional latency. Plus, it's versatile across different architectures like GPT-2, GPT-3, and Roberta, making it adaptable for various tasks. And let's not forget its impact on accessibility. Lowering GPU memory usage during training by up to 3 times really makes a difference for researchers with limited hardware.
So, in terms of what's coming up today, we'll be covering the problem LoRA addresses, its unique approach to model adaptation, and how it stacks up against other methods. We'll also look at some empirical results that demonstrate its effectiveness.
That's right. And as we navigate through LoRa's core concepts, keep in mind how its strategies echo the broader goal of making large models more adaptable with fewer computational demands.
Sounds like a great session ahead. I'm excited to get into the details and see how LoRA fits into the bigger picture.
Perfect. Let's jump right into the main discussion and uncover the fine-tuning efficiency that LoRA brings to the table. Today, we'll begin by exploring the introduction of low-rank adaptation, or LoRA. LoRA is an approach to make fine-tuning large language models more efficient. It's about reducing computational costs while maintaining performance by modifying only a small set of parameters instead of all of them. Let's break down the key ideas step by step. To start, LoRA addresses the challenge of adapting large-scale, pre-trained language models. Can you explain why this is necessary?
I believe it's because models like GPT-3, which have billions of parameters, are too large to fine-tune completely for every new task. The process becomes expensive and inefficient.
Exactly. Fine-tuning such massive models can be prohibitively costly, both in terms of storage and hardware requirements. Instead of retraining all the parameters, LoRA focuses on modifying just a small subset. Specifically, it uses low-rank matrices to update the model. Do you have any idea what a low-rank matrix is?
A low-rank matrix is one with fewer linearly independent rows or columns compared to its dimensions. So, by using these matrices, LoRA can simplify the updates needed for the model.
That's correct. In LoRA, the updates to the model weights are represented using low-rank matrices. This approach reduces the number of trainable parameters drastically while keeping most of the original model weights frozen. This strategy is both memory and compute efficient. Let's move on to the practical benefits of this approach. LoRA not only reduces the computational load, but also makes task switching more efficient. What do you think this means in terms of real-world applications?
I guess it means that you can use a single pre-trained model for various tasks without having to store multiple versions. You just load the small, low-rank matrices for each task, which saves space and time.
Precisely. The modular design of LoRA allows for quick adaptation across tasks by loading different low-rank matrices, making it versatile and cost-effective. It's a significant improvement over traditional fine-tuning, especially when deploying models in real-time applications. To sum up, the introduction part of LoRA highlights its main goal: achieving efficient adaptation of large language models by updating a small set of parameters using low-rank matrices. This approach maintains model performance while reducing the computational burden, making it an appealing choice for various applications. Now that we've discussed the basics of LoRA, let's transition into the problem it aims to solve. We'll look at the challenges associated with adapting large-scale language models for different tasks. This section is called Problem Statement. The main problem with full fine-tuning is that it involves updating every parameter of a large, pre-trained language model. Imagine trying to adapt a model as large as GPT-3, which has around 175 billion parameters. As churches. What do you think happens when we try to fine-tune it for multiple tasks?
I guess you'd need to store a separate model for each task, which would require a massive amount of storage and memory.
Exactly. That's one of the biggest challenges. Storing and deploying many independent, fine-tuned versions becomes impractical. For each task, you end up with a different set of updated parameters, making it hard to scale across multiple applications. Let's consider another issue: the computational cost of full fine-tuning. Each parameter update requires significant hardware resources. How do you think this affects model adaptation?
I think it makes it difficult for organizations without advanced hardware setups to adapt these models for specific tasks, since they might not have enough computational power.
That's correct. The high hardware requirements make it less accessible for many researchers and developers. This is where LoRA's parameter-efficient approach comes into play. Instead of updating all parameters, it focuses on a smaller subset, significantly reducing the need for hardware and making model adaptation more feasible. To sum up, the problem statement identifies two major issues with traditional fine-tuning: high storage requirements and substantial computational costs. LoRA aims to tackle these challenges by using a more efficient method of model adaptation. We've established the main problem LoRA aims to address, but it's natural to wonder, aren't the existing solutions good enough? In other words, why do we need LoRA when we already have various methods for model adaptation? Historically, two main strategies have been used to adapt large language models efficiently: adding adapter layers or optimizing input activations. Both have their own benefits and limitations. Can you briefly describe what adapter layers do?
Sure. Adapter layers are small neural networks inserted between existing layers of a model. They help make the model adaptable to new tasks without changing the main weights significantly.
Exactly. Adapter layers are a popular method due to their parameter efficiency, but they introduce an additional challenge: inference latency. Because adapter layers process sequentially, they can slow down real-time applications. Interrupt. Do you see why this could be problematic, especially in a large-scale deployment?
Yes, that makes sense. If the inference becomes slower, it could affect applications where response time is critical, like chatbots or search engines.
Correct. Now let's consider the other strategy: optimizing input activations. This method adjusts how input data is processed rather than modifying the main model weights. It's effective to some extent, but what drawback do you think it has?
I suppose it might limit the usable sequence length since additional tokens are used for tuning. That could reduce the space available for the actual task data.
Exactly right. Both approaches have their trade-offs, making them less ideal for large-scale and latency-sensitive scenarios. LoRA, on the other hand, uses low-rank matrices to achieve efficient model adaptation without the added latency or sequence limitations. This approach combines the best of both worlds: reduced parameter requirements and no impact on inference speed. To sum up, existing solutions provide partial answers to the challenge of efficient model adaptation, but they fall short in large-scale, real-time applications. LoRA's low-rank adaptation offers a promising alternative by addressing the core limitations of these methods. With a good understanding of the challenges existing solutions face, let's now delve into how LoRA's method works specifically. This involves the concept of low-rank parametrized update matrices and its application to transformers. LoRA modifies the weight matrices of neural networks using a low-rank decomposition during adaptation. Essentially, instead of updating the entire weight matrix, we break it down into two smaller matrices, B and A, where B is multiplied by A to form the update matrix. Do you understand how this decomposition helps reduce the number of trainable parameters?
I think so. By using lower rank matrices, we limit the changes to fewer parameters, making training more efficient. It's like compressing the update without losing the important information.
Exactly. This low-rank decomposition enables efficient updates while keeping the pre-trained weights frozen. It allows for the same expressiveness as full fine-tuning, but with significantly fewer parameters. The benefit is not just efficiency, but also a reduction in memory and computational load during training. Now let's explore how LoRA applies to transformer models, which are the backbone of many large language models. In a transformer, there are multiple weight matrices, particularly in the self-attention mechanism, including query, key, value, and output matrices. LoRA primarily focuses on adapting these matrices. Do you know why this choice is made?
I guess it's because these matrices play a critical role in the model's ability to understand and generate text. So adapting them effectively can improve task performance.
That's correct. By concentrating on these attention weights, LoRA captures task-specific information more effectively. The query and value matrices, in particular, show the best results when adapted using LoRA. It's important to note that this approach does not introduce additional latency during inference, because the low-rank updates can be merged with the original weights. To summarize, LoRA employs low-rank matrices to efficiently update model weights, reducing the number of trainable parameters while preserving model performance. Its application to transformers specifically targets the attention weights, making the adaptation both effective and scalable. Now that we've explored LoRA's adaptation mechanism in transformers, let's shift our focus to the empirical results. This next part will cover the baseline methods and LoRA's performance on different models, specifically Roberta base/large and Roberta XXL. In order to evaluate LoRA's effectiveness, we first need to understand the baselines. The baseline methods include full fine-tuning, which updates all model parameters, and other parameter-efficient techniques like bitfit, adapters, and prefix tuning. Why do you think it's important to compare LoRA with these methods?
I think comparing with these baselines helps us understand whether LoRA truly offers a significant improvement in efficiency and performance, right?
Exactly. The comparison shows how LoRA stacks up in terms of both reducing trainable parameters and maintaining model performance. In many cases, LoRA not only matches but also exceeds the performance of these baselines, while using fewer trainable parameters. Moving to the Roberta model results, we have two versions, Roberta base and Roberta large. LoRA achieves competitive results on GLU benchmark tasks, often surpassing fine-tuning with much lower memory requirements. Can you explain why this is significant for practical applications?
If LoRA can achieve similar or better performance with fewer resources, it becomes more practical for real-world use, especially for organizations with limited computational power.
Precisely. The fact that LoRA can deliver robust performance while being lightweight makes it highly suitable for diverse NLP applications. Now let's look at Roberta XXL, which is a larger model compared to Roberta. Even with Roberta XXL, LoRA maintains strong results, matching full fine-tuning in tasks like GLUE without the need for extensive hardware. In summary, LoRA demonstrates clear advantages over traditional methods across different models, whether it's Roberta or Roberta. It achieves high performance while keeping the number of trainable parameters low, making it a versatile and efficient choice for NLP tasks. After understanding LoRA's performance on models like Roberta and Roberta, let's now shift our focus to GPT models. We'll first explore LoRA's results on GPT-2 medium and large, and then discuss its performance when scaled up to GPT-3175B. Starting with GPT-2, LoRA was tested on both medium and large versions, primarily focusing on natural language generation tasks. It achieved competitive results across several benchmarks, including the E2ENLG challenge, demonstrating a notable boost in metrics like BLEU, Rouge-L, and Meteor, while maintaining a lower number of trainable parameters. How do you think this impacts the practicality of using GPT-2 models in resource-constrained environments?
I think the lower number of trainable parameters would reduce both memory usage and computation time, making GPT-2 more feasible for real-time applications or deployment in environments with limited hardware.
Exactly. The efficiency gains not only make GPT-2 more practical, but also help maintain strong performance. Now, let's move on to scaling LoRA to GPT-3 with 175 billion parameters. Spray. This is a significant step, considering the massive scale of GPT-3. LoRA was tested on a range of tasks, including WikiSQL, multi-NLI, and SAMSUM, matching or even surpassing the performance of full fine-tuning. What do you think is the most significant advantage of using LoRA at this scale?
I'd say the most significant advantage is the drastic reduction in computational cost and memory requirements. It's impressive that LoRA can achieve similar or better results while being much more resource efficient.
Absolutely. With LoRA, the number of trainable parameters was reduced by up to 10,000 times, significantly decreasing VRAM consumption and making it feasible to adapt GPT-3 on fewer GPUs. Moreover, LoRA does not add any inference latency, making it suitable for large-scale deployments. This is a crucial factor when working with models of this magnitude. To sum up, LoRA proves to be highly effective for adapting GPT-2 and GPT-3 models, maintaining performance while significantly reducing the computational load. This positions it as a strong candidate for large-scale language model adaptations. Now that we've seen how LoRA performs on different models, it's helpful to understand how it fits within the broader context of related works in the field. We'll dive into some of the foundational works that have inspired or paralleled the development of LoRA. The evolution of large language models has been closely tied to the transformer architecture, introduced by Vaswani et al. In 2017. Transformers have become the backbone of models like BRT, GPT-2, and GPT-3, and have significantly influenced NLP research. Do you remember how transformers primarily utilize self-attention mechanisms?
Yes, self-attention is crucial for allowing models to capture long-range dependencies in text. It helps the model understand relationships between words in a sequence, regardless of their distance from each other.
Exactly. This sequence-to-sequence architecture, particularly in the autoregressive setting like GPT-2 or GPT-3, has enabled state-of-the-art performance in various NLP tasks. However, adapting these models efficiently has been a challenge, leading to several parameter-efficient techniques such as adapter layers and prefix tuning. Do you recall how these techniques generally work?
Adapter layers introduce additional parameters within the existing model layers to focus on specific tasks, while prefix tuning involves adding task-specific tokens to the input embeddings.
That's correct. Both methods aim to fine-tune large models without updating all parameters, making them more efficient. However, they can introduce latency or limit usable sequence length, which impacts performance in real-time applications. This is where LoRA stands out. It merges the efficiency of low-rank updates with the benefits of parameter sharing, minimizing latency. Further inspiration for LoRA comes from low-rank adaptations in other domains, where low-rank matrices have been used to approximate dense weight updates in neural networks. This concept has been applied to improve computational efficiency in various deep learning tasks, showing that many neural networks naturally exhibit low-rank properties during training. To sum up, LoRA builds upon these earlier approaches while addressing their limitations. By applying low-rank updates directly to frozen pre-trained weights, it achieves efficient task adaptation with minimal resource overhead, making it a versatile method in the NLP landscape. Building on our understanding of LoRA's application to transformers, let's discuss a crucial question. Which weight matrices should LoRA be applied to within the transformer architecture to achieve optimal results? In a transformer model, there are several key matrices in the self-attention mechanism: the query, key, value, and output matrices. Among these, applying LoRA to the query and value matrices tends to yield the best performance across tasks. Why do you think this might be the case?
I'd say it's because the query and value matrices directly influence how the model attends to different parts of the input. Adapting these weights would likely have a more significant impact on the model's ability to capture relevant information.
Exactly. The query and value matrices are central to the self-attention mechanism, so adapting them helps the model better capture task-specific patterns. Empirical studies show that adapting both the query and value matrices results in higher validation accuracy compared to focusing on just one type of matrix, given the same parameter budget. Additionally, LoRA's low-rank adaptation makes it possible to update these matrices without increasing the inference latency. This allows for efficient adaptation without compromising the model's performance or speed. To sum up, the optimal strategy is to apply LoRA to the query and value matrices, as this approach strikes the right balance between efficiency and effectiveness in task adaptation. As we've seen, selecting the right matrices to adapt with LoRA is essential for optimal performance. Now let's explore another key question. What is the optimal rank, R, for LoRA? The rank, R, in LoRA determines the size of the low-rank matrices used for adaptation. In practice, a lower rank can significantly reduce the number of trainable parameters, but it raises the question of whether this reduction compromises performance. Can you think of any potential trade-offs when setting a lower rank?
I imagine that setting a very low rank could limit the model's capacity to learn new patterns, which might lead to reduced accuracy in certain tasks.
That's right. While a lower rank does help reduce computational requirements, it might not capture enough task-specific information. However, interestingly, experiments have shown that even a rank as small as 1 or 2 can be surprisingly effective for some tasks, particularly when adapting both the query and value matrices in transformers. In tests with models like GPT-3 and GPT-2, it was observed that LoRA performs competitively with a very small rank. For instance, in tasks like Wiki-SQL and Multi-NLI, a rank of 4 was found to deliver strong results. Can you explain why this might suggest that the adaptation matrix has a low intrinsic rank?
It seems like the changes required for task adaptation are relatively minor, meaning that even a small rank can capture the essential differences needed for specific tasks.
Exactly. This supports the hypothesis that adaptation matrices may have a low intrinsic rank, focusing mainly on amplifying task-specific directions that aren't emphasized in the original pre-trained weights. Thus, increasing the rank beyond a certain point doesn't necessarily improve performance, as it doesn't capture more meaningful subspace. To summarize, while the optimal rank for LoRA depends on the specific task and dataset, a surprisingly low rank often suffices, especially when adapting multiple weight matrices. This highlights the efficiency and flexibility of LoRA's low-rank adaptation approach. We've discussed how the optimal rank R plays a significant role in LoRA's performance. Now let's consider how the adaptation matrix delta W compares to the original weight matrix W. This will help us understand what exactly is being captured or amplified during adaptation. The relationship between delta W and W is critical to understanding LoRA's adaptation mechanism. In essence, delta W represents the changes made to W during fine-tuning. One of the main questions is whether delta W highly correlates with W. What do you think this means in terms of model adaptation?
If delta W is highly correlated with W, it might suggest that LoRA is simply amplifying existing features in W rather than introducing new task-specific directions.
That's an insightful observation. Interestingly, empirical studies show that delta W does not predominantly amplify the top singular directions of W. Instead, it amplifies directions that are not emphasized in W, suggesting that these directions are more task-specific and essential for adaptation. For example, in GPT-3, the overlap between delta W and W is relatively low, indicating that LoRA adapts to more nuanced features. Moreover, when we look at the amplification factor, essentially how strongly delta W boosts these less emphasized directions, we find that this factor can be quite large. For instance, with a rank of 4, the amplification factor reaches up to 20, indicating significant changes in specific task-relevant directions. Does this make sense in terms of how adaptation works in LoRA?
Yes, it seems that the adaptation matrix isn't just repeating what's already in the model but is focusing more on task-specific elements, which helps improve task performance efficiently.
Exactly. The low correlation between delta W and W reinforces the idea that LoRA introduces critical adjustments to better fit specific tasks, rather than merely boosting existing features. This allows LoRA to achieve effective adaptation with minimal changes, highlighting its efficiency in fine-tuning large models. In summary, the adaptation matrix delta W is designed to amplify directions that are not already emphasized in W, providing targeted adjustments for task adaptation. This low correlation with W demonstrates LoRa's ability to focus on task-specific changes while maintaining overall parameter efficiency. As we wrap up our discussion on LoRa, it's time to reflect on the overall conclusions of this work as well as potential directions for future exploration. LoRa provides a significant solution to the challenges of fine-tuning large language models. It achieves efficient adaptation by applying low-rank updates, which helps maintain model quality without increasing inference latency or reducing input sequence length. This makes it not only resource efficient but also effective for fast task switching in deployed environments. How would you summarize the most impactful aspect of LoRa based on what we've covered?
I think the most impactful aspect is how LoRa allows for efficient adaptation of large models by focusing on a small subset of parameters, making it accessible and practical for a wider range of users and tasks.
That's a good summary. Indeed, the ability to train just a small set of parameters while keeping the majority of the model frozen is what makes LoRa particularly versatile. Its principles are applicable not just to transformers, but to any neural network with dense layers, making it a broadly useful adaptation strategy. Looking ahead, there are several promising directions for future work. For instance, combining LoRa with other efficient adaptation techniques could yield even better results. Deterrence. Additionally, understanding the underlying mechanisms of how LoRa transforms pre-trained weights into task-specific adaptations remains an open research area. Are there any other future directions that come to your mind?
I think exploring more principled ways to select which weight matrices to apply LoRa to could be another direction, as this seems to rely on heuristics at the moment.
Exactly. Finding more systematic methods for choosing weight matrices and further investigating the ranked efficiency of the adaptation matrices could offer deeper insights into model adaptation. Additionally, the ranked efficiency observed in delta W suggests that the pre-trained weight matrix W might be ranked efficient too, which could inspire new approaches in adaptation strategies. To conclude, LoRa represents a step forward in making large language models more adaptable, accessible, and efficient. It opens up various avenues for further exploration, aiming to enhance our understanding and application of neural networks in different contexts. Well, that wraps up our discussion on LoRa. We covered a lot, from how it reduces trainable parameters using low-rank matrices to its versatility across models like GPT-2, GPT-3, and Roberta. Plus, its efficiency in both memory usage and inference speed makes it a standout in model adaptation strategies.
Definitely. I found the idea of keeping the pre-trained weights frozen while still achieving effective fine-tuning really interesting. And the fact that it doesn't add any inference latency? That's a big deal.
Absolutely. It's been great revisiting this method, especially considering how it complements recent advancements in scaling and memory efficiency.
I agree. It was a great conversation, and I hope our listeners found it as insightful as we did.
Thanks everyone for tuning in. We appreciate your time, and we hope you enjoyed today's deep dive into LoRa.
And if you have any questions or thoughts, don't hesitate to reach out. See you next time.
See you